Hello guys, welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course on hydrogen, and I hope you enjoyed the first lecture with me. So today we begin with lecture 2 from the course, but make sure you watch the previous one before viewing this one. In the previous lecture, while we were talking about the position of hydrogen in the periodic table, we discussed that hydrogen's electronic configuration is quite similar to both alkali metals as well as halogens. So in this lecture, we would be continuing our discussion further and see how hydrogen is similar yet different from both alkali metals as well as halogens. So we will be taking a comparison of hydrogen with the alkali metals and halogens in this lecture. So we will be continuing our discussion from where we left it in the last lecture. We were discussing about the position of hydrogen in the periodic table, and I was telling you that the position of hydrogen in the periodic table is a matter of controversy. Why it is a controversy is because that hydrogen is a non-metal, but it has been placed in the periodic table along with alkali metals in group 1, which are typical metals. Why is it so? You all know now that the electronic configuration of hydrogen, which is 1s1, this is quite similar to that of alkali metals, which have the general electronic configuration as ns1. Lithium having 2s1, sodium having 3s1. These are all having similar electronic configuration to that of hydrogen, and that is why hydrogen is placed in group 1 with the alkali metals. But hydrogen, it also has an electronic configuration similar to that of halogens. Why halogens? Well, halogens, if you look at the electronic configuration, this is Ns2Np5, no resemblance. There is a little resemblance. What is that resemblance? Halogens, if you look at the electronic configuration, they are just one short of the nearest noble gas configuration, that is Ns2Np6. Similar to the halogens, hydrogen also requires just one electron to reach up to the nearest noble gas configuration of helium, which has the electronic configuration of 1s2. So therefore, hydrogen has properties similar to that of alkali metals as well as of halogens, because the electronic configuration of hydrogen is similar to both of these. Right? And we know from the understanding of the periodic classification of elements that if the electronic configuration is the same, well, the chemical properties of the elements, they are going to be the same. So we will have a close look one by one how hydrogen is similar to alkali metals, how it is similar to halogens, and then we will be taking up the differences of hydrogen from both of them also. We will begin with the similarity of hydrogen to the alkali metals. So the first similarity of hydrogen with alkali metals is obviously its electronic configuration, which we have just now discussed. The general electronic configuration for both hydrogen and alkali metals is the same, that is Ns1. Hydrogen is 1s1, lithium is 2s1, sodium is 3s1, potassium is 4s1, rubidium is 5s1. So all having the general electronic configuration Ns1. The next similarity is the electronegativity. If you look at hydrogen and the alkali metals, all of these, they have a tendency to lose one electron to form the respective monovalent cation. For example, if you look at sodium, sodium can lose one electron and form Na positive. And similar to this, hydrogen also loses one electron and forms H positive. So both hydrogen and alkali metals, they exhibit electropositive character. Right? The next similarity is in the oxidation state and the valency of these. We see that both hydrogen and alkali metals, they exhibit a valency and oxidation state of +1. For example, if you look at HCl, NaCl, KCl, in all of these, what are you seeing? That the oxidation state as well as the valency of hydrogen, sodium and potassium is going to be +1. Next we have is a similarity in their reducing nature. If you look at hydrogen and alkali metals, they all are strong reducing agents. For example, if we have hydrogen reacting with Fe3O4, we find that hydrogen acts as a strong reducing agent. It reduces Fe3O4 to Fe. And similar to this, if you look at sodium, this also reacts with B2O3. It acts as a strong reducing agent and reduces B2O3 to boron. So both hydrogen and alkali metals, they are strong reducing agents. Next we have is a similarity in the electrolysis of the salts of these. So what we see is that on electrolysis of the salts, for example, chlorides, hydrogen and alkali metals both are liberated at the cathode. For example, when there is an electrolysis done for NaCl solution, what we see is that sodium is liberated at the cathode and chlorine on the anode. Similar to this, if we see HCl, there we find that H2 is going to be liberated at the cathode and again chlorine will be liberated at anode. So on the electrolysis of these salts, hydrogen and alkali metals both are being liberated at the cathode. So next similarity we have is the reaction with the electronegative elements. We just now studied that both hydrogen and alkali metals, they are electropositive in character. Therefore, when they react with electronegative elements, or you can say the non-metals, what we see is that they form the corresponding oxides, sulfides, chlorides, etc. With oxygen, you can see that hydrogen is going to react to form H2O. Similar to this, the alkali metals Na2O, K2O. Fine. So next we see is the reaction with sulfur. So with sulfur, hydrogen is forming the corresponding sulfide H2S. Similar to this, the alkali metals will be forming the sulfides Na2S, K2S. And if you look at a reaction with the halogens, what you will be seeing is that hydrogen forms the corresponding halides HX. And also the alkali metals, they will be forming the corresponding halides like NaX, KX. So the reaction with the electronegative elements is also similar to both the alkali metals and hydrogen. So now you have seen that hydrogen resembles quite a lot in its properties with the alkali metals. So here we have a chart for you, giving you the complete detailed discussion that we've just now had in the form of a chart, so that when you're revising your concepts, well, this takes less of a time. So hydrogen and alkali metals resemblance chart it is, right? So we have already discussed the electronic configuration, the electronegativity, both of them being electropositive in character, oxidation state for both of them being +1, reducing nature, both of them being strong reducing agents, both of them being liberated at the cathode when an electrolysis of the hydrides and the alkali metal salts are done. And similarly, we have also discussed that when they are going to react with the non-metals or the electronegative elements, they are forming the corresponding oxides, sulfides, halides, etc. So this is a complete chart of what we have just now discussed for a quick revision for you people. So next we discuss the differences of hydrogen from the alkali metals, and the first point of difference is the physical state. Hydrogen is a gas at room temperature, whereas alkali metals, they are solids. The next point of difference is the non-metallic nature of hydrogen. Hydrogen is a non-metal, whereas alkali metals, they are typical metals. The next is the atomicity. Well, hydrogen, this exists as a diatomic gas in the form of H2. Whereas alkali metals, they are monoatomic in the vapor state. They are existing in the form of atoms in the vapor state like lithium, sodium, potassium. Whereas hydrogen is not existing in the form of atoms. It is existing in the form of a molecule, which is a diatomic molecule, H2. Fine. The next we have is the nature of compounds, which is different. If we look at the compounds of hydrogen, hydrogen generally forms covalent compounds, whereas alkali metals, they form ionic compounds. So the next difference is in the ionization enthalpy values for hydrogen and the alkali metals. So I hope you all remember what is ionization enthalpy. We discussed it in detail while we were talking about the periodic classification of elements. In case you have forgotten, you do not remember, please you can go back to the playlist from us. There is a detailed course on the periodic classification of elements, and you can have a detailed understanding of the ionization enthalpy, the trends for ionization enthalpy, enthalpy in the periodic table, right? But now if I quickly revise that with you, ionization enthalpy is that amount of energy which we require to remove one valence electron from an isolated neutral gaseous atom. Right? So if we look at the values of ionization enthalpy for hydrogen, it is 1312 kilojoule per mole. For lithium, it is 520 kilojoule per mole. Sodium, it is 418 kilojoule per mole. For lithium, sodium, and the rest of the alkali metals, these values, they are quite low. But in comparison to the alkali metals, the value for hydrogen, this is quite high. Right? So hydrogen, this has a high ionization enthalpy in comparison to the alkali metals. Now the question is why? So hydrogen, you all know that this has an extremely small size. And an extremely small size makes it very difficult to remove one electron because that electron is very tightly held to the nucleus. So we require a lot amount of energy to remove that electron which has been tightly held to the nucleus in case of hydrogen. Right? So we see the value of ionization enthalpy for hydrogen much higher as compared to the alkali metals. Now the next point of difference is in the size of the cation. So when hydrogen is going to lose one electron, it is going to form H positive. Similarly, lithium will be forming Li positive, sodium will be forming Na positive. So what we see is the size of H positive ion is going to be much smaller than the size of the cations for the alkali metals. Again, why is it so? You all know that hydrogen has just one electron. So when we are going to remove that one electron, what is going to be left behind? Only the nucleus, right? There is just one proton for hydrogen, and H positive is nothing but actually a proton only. So you have to remember what is H positive. Well, it is nothing but a proton. Fine. And proton, you all know this is an extremely small sized particle. So if we compare the size of the cations for hydrogen and the alkali metals, you are going to say what? The hydrogen ion, this is extremely small in size as compared to the alkali metal ions, which are going to be larger in size. Now, when we are talking about the size of the H positive ion, this is very important for you to remember. Here is this also, that this H positive, this is so small in size that it is incapable of independent existence. So if we look at many of the reactions which are going to happen in water, right? So water is going to be the solvent. For example, when we talk about the acid-base reactions, there we always say that the acid is going to break up into H ions, and for example, if we talk about HCl, so it will be H ions plus chloride ions. So do that H ions exist independently in water? No, they do not. These H ions, they combine with water to form H3O positive, which is called as the hydronium ion. So do remember that H positive does not have an independent existence. Whenever it is going to be present in water, it is going to combine with water, and what we will be having is hydronium ion. Never it will be H positive. We just write it for the sake of convenience that it is H positive and chloride Cl negative. When we talk about HCl, or if we are talking about H2SO4, it is going to be H positive plus sulfate ions. But it is always going to be hydronium ion which we will be seeing. H positive does not have an independent existence of its own. So once again, let us quickly tabulate the differences of hydrogen from the alkali metals so that you can quickly revise them when you are preparing for your examinations. So hydrogen, it is a gas at room temperature, whereas alkali metals, they are solids. Hydrogen is a non-metal, alkali metals, they are typical metals. It is a diatomic molecule, whereas alkali metals, monoatomic in the vapor state. The nature of compounds, hydrogen, they are mostly covalent, whereas for alkali metals, they are going to be mostly ionic compounds. Ionization enthalpy of hydrogen, which is 1312 kilojoule per mole, is quite high as compared to the alkali metals. Again, H positive, this is very small. It is having an empty 1s orbital, it cannot exist independently, and when it is going to be present in combination with water, it is always going to be existing as H3O positive, whereas alkali metal ions, they are large ions existing as Na positive, K positive. Next, we discuss the similarity of hydrogen with the halogens. And here again, we will be starting with the electronic configuration first of all, right? So we've already discussed that the electronic configuration of hydrogen is 1s1, and this is one electron less than the nearest noble gas, which is helium, with the electronic configuration of 1s2. Let us look at the group 17 elements now. First, we have the first halogen that we have is fluorine. So fluorine has the electronic configuration of 2s2 2p5. This is also one electron less than the nearest noble gas neon, which has the electronic configuration 2s2 2p6. So similar to fluorine, all the halogens, they have the general configuration of ns2 np5, which is going to be one electron less than the nearest noble gas with the configuration ns2 np6. So here we have a similarity of the electronic configuration of hydrogen to the halogens, both being one electron less than the nearest noble gas configuration. Now, when the configurations, they are again similar, we will be seeing some similarities in the chemical properties of hydrogen to the halogens as well. So first of all, let us see the electronegative character. The electronegative character is similar for both hydrogen and the halogens. They both have a tendency to gain one electron. And why they have a tendency to gain one electron? Because by this, they will be achieving the nearest noble gas configuration. So by gaining one electron, hydrogen will be forming H negative, and halogens, they will be forming X negative respectively. And thus they both exhibit a electronegative character. Fine. Now the next we have is the ionization enthalpy. Just now we saw that the ionization enthalpy values for hydrogen, they are quite high as compared to the alkali metals. But when we look at the values for hydrogen and the halogens, well, these values, they're quite comparable. We have hydrogen having the value of 1312 kilojoule per mole. Fluorine, it is 1680 kilojoule per mole. For chlorine, this is 1255 kilojoule per mole. So these values, they're quite comparable, whereas there was a difference in the values for hydrogen and the alkali metals, right? The next we have is the similarity in the oxidation state. So like halogens, hydrogen also exhibits -1 oxidation state in some of its compounds. For example, if you see sodium hydride, here hydrogen is exhibiting an oxidation state of -1, and this is similar to the oxidation state of chlorine in NaCl, right? So here chlorine is having oxidation state of -1, here hydrogen is having an oxidation state of -1. So it is quite similar in the oxidation state to the halogens. The next we have is the atomic state. So hydrogen, this exists as a diatomic molecule H2. Similar to this, we have the halogens existing as F2, Br2, Cl2, and so on, right? So the atomic state of hydrogen and halogens, this is the same. Whereas when we talked about the alkali metals, I hope you remember, they were existing as in the monatomic form in the vapor state, whereas hydrogen, this exists as a diatomic molecule. Fine. So the next similarity is in the electrolysis of the hydrides and the halides, where what we see is that both halogens and hydrogen, they are liberated at the anode. For example, in the electrolysis of the sodium hydride solution, we find sodium being deposited at the cathode and hydrogen being liberated at anode. Similar to this, we have the electrolysis of sodium chloride solution, sodium at the cathode and chlorine at the anode. The next similarity is in the occurrence of the physical nature of these elements. What we see is that both hydrogen and halogens, they exist as gases. For example, hydrogen, chlorine, fluorine, they are all gases at room temperature. Reaction with the electropositive elements, what we see is that when hydrogen and halogens, they combine with the S block elements, they form the corresponding hydrides and halides. For example, when sodium and hydrogen, they are combining, it is forming sodium hydride. And when sodium is going to combine with chlorine, it is going to be sodium chloride. When it is going to react with bromine, it is going to be sodium bromide, and so on. Next similarity is in the reaction with the nonmetals, where we see both hydrogen and halogens, they forming covalent compounds. For example, you can see that carbon and hydrogen forming methane, CH4, and here with halogens it is CCl4, right? Next we have nitrogen plus hydrogen forming ammonia, and nitrogen and chlorine, as you can see, is forming NCl3, similar, right? And then we have hydrogen plus oxygen forming H2O, and chlorine and oxygen forming ClO2. So these all compounds, either we have with hydrogen or with halogens, the non-metals, they are forming covalent compounds. So again, we have put this all in the form of a chart so that you can revise them very quickly, retain them well, and excel in your examination. The electronic configuration of hydrogen being similar to halogens, they are going to be 1 electron less than the nearest noble gas configuration. Both they form hydrides and halides forming uninegative ions. So we are seeing there is a similarity in their electronegative character. Ionization enthalpy values, they are comparable. Oxidation state we can see is again -1 for both of them. Both are forming diatomic molecules, and during the electrolysis both being liberated at the anode, both occurring as gases in nature. Then the reaction with electropositive metals forming hydrides and halides respectively, similar behavior we see, and again both of them with the non-metals form covalent compounds. So next we move on to the difference from the halogens, where we will be discussing 2 points of difference, one related to the reactivity and other related to the lone pair of electrons. So first talking about the reactivity. Now we know that hydrogen and halogens, both they have a tendency to gain 1 electron to achieve the nearest noble gas configuration. And as a result, halogens, they will be forming a halide ion, right? So X plus electron is going to form X negative, and similar to this, hydrogen will be gaining 1 electron and forming H negative. What we see is that there is a difference in the reactivity. Halogens form the halide ion more readily than hydrogen forming the hydride ion, and this is owing to the lesser tendency of hydrogen to gain the electron due to its much smaller size as compared to the halogens. The incoming electron is repelled by the electron which is already present in case of the small sized hydrogen. Fine, I think this is clear. Now the next reference is in the presence or the absence of lone pairs. So what do we see is that if you look at the molecule of a halogen, we are seeing the molecule of a chlorine now, there are going to be 3 lone pair of electrons present per atom. But when we compare this to hydrogen, there is no lone pair of electron present. So halogens, they possess 3 pairs of unshared electrons, while hydrogen does not have any lone pair of electrons. So this is also one of the differences hydrogen has from halogens. Now all this discussion that we have done in this lecture, we have seen that hydrogen, this is similar to alkali metals. In some respects, it is similar to the halogens. In another respect, it is differing from the alkali metals. It is also having some differences from the halogens. So what do we conclude over here? What we conclude is that hydrogen is a unique element, right? And when we are placing this with group 1 elements, we should not be placing it with group 1 elements, neither should we placing it with the halogens, because it is having similarities and also dissimilarities from both these group of elements. So what we should be doing is that we should be regarding hydrogen as a separate group in itself. And generally now we are seeing also that in some of the periodic tables it has started coming that hydrogen is placed in the center of the periodic table, neither placed with group 1 elements, neither placed with group 17 elements. Now, this is as far as the discussion of this lecture is concerned. Now, as you've seen in the previous lecture, we will be seeing a few multiple choice questions in this lecture also. Let us see how much you have understood from this lecture. And when you are going to see the questions, please do post your answers in the comment section. So again, this will be 5 multiple choice questions which I will be asking you, for which I want you and request you all to put your answers in the comment section. The first question, this is from the NCERT exemplar book, and I request you all here that please do attempt all the questions from the NCERT exemplar as well as the NCERT back exercises, because this is going to be very important for you to excel in any of your examinations. So the first question is, hydrogen resembles halogen in many respects for which several factors are responsible. Of the following factors, which one is most important in this respect? The first question is its tendency to lose an electron to form a cation, its tendency to gain an electron in its valence shell to attain stable electronic configuration, its low negative electron gain enthalpy value, its small size. The next question is, why does H positive ion always get associated with other atoms or molecules? For the first choice is the ionization enthalpy of hydrogen resembles that of alkali metals. Its reactivity is similar to halogens. It resembles both alkali metals and halogens. Loss of an electron from hydrogen atoms results in a nucleus of very small size as compared to atoms or ions. Due to small size, it cannot exist free. And again, this is from the NCERT exemplar book. The next question is, which of the following statements are true for hydrogen? The first choice, it exists as a diatomic molecule. It has one electron in the outermost shell. It can lose an electron to form a cation which can freely exist. It forms a large number of ionic compounds by losing an electron. Please remember, for this question there are going to be multi-correct answers. There are going to be more than one choices which are going to be correct. So please do attempt it accordingly. The fourth question is, in which of the following properties hydrogen does not show similarity with alkali metals? First, electronic character, reducing nature, electronic configuration, diatomic nature of the molecule. The fifth question is, in what respect electronic configuration of hydrogen and halogens they are similar? The first choice is hydrogen and halogens, they have one electron in the outermost shell. Hydrogen and halogens have one electron less than the nearest noble gas configuration. Hydrogen and halogens have noble gas configuration. And the last choice is hydrogen and halogens can lose one electron to form positive ions. So please, these are 5 questions and you have to put your answers in the comment section. The more you attempt the questions, the better you are going to be. So please do put in your answers to get the correct answers from my end also. So that would be all for this lecture, and in the next lecture we will be talking about the isotopes of hydrogen. This is going to be a very important topic for you because many examination questions they are coming from this topic. So I hope you do not want to miss that, and for that you just simply have to subscribe to the channel and click on the bell icon so that you get a notification the moment we put up the next lecture for you. If you've liked this lecture, please do click on the like link. Thank you and have a nice day. God bless you.